Hello students, how are you all doing? Welcome to our channel physics class. Today we'll study magnetism and matter. So what is magnetism? The property that is related to the magnet is known as magnetism. And how it exists in matter, how it affects matter, what are the properties related to the magnetism of matter, that all comes under this unit. So we will start up with magnetism. Magnetism is really a very fascinating thing because we can observe magnetism in our own Earth, in our own planet Earth, because Earth also behaves as a magnet. So we'll study all the properties related to this magnetism and the Earth magnetism. So first of all, we'll study some points that we observe as a proof of a magnetism, that is a daily observation related to magnetism. First of all, we'll start up with the magnetism observed. Just take a bar magnet, and this is how a bar magnet is represented. So if we suspend this bar magnet freely, then it always points in the north-south direction. You might have seen your magnetic compass, and that we always use to find out the direction. But what you see that if you are stuck up with the direction or you want to confirm the direction, or nowadays we use our smartphones to find out the directions. So that is all the magnet property. So if you suspend a bar magnet freely, then it always points in the north-south direction. Here capital N stands for north and capital S stands for south. Also, do you know that this N also points toward geographical north, and the south of the bar magnets points out to the geographical south. Now, what is this geographical north and geographical south? Yes, these are the simple our North Pole and South Pole. So if we draw our Earth in a very simple way, say this is the North Pole and this is our South Pole. So the north tip of this bar magnet points to geographical north, that is our North Pole, and the south tip of this bar magnet points us to geographical south, that is our South Pole. As simple as that. Now second point. Now we know the property of a bar magnet. So if we take two bar magnets, so these are the two bar magnets, and we try to bring them together. This arrow shows the direction. If we try to bring them together, then what happens? If the south of one comes near to the north of the other, then they are attracted towards each other. That means there is an attractive force. So whenever there are two different poles of the bar magnet bring together, then there are always a force of attraction. But what happens if two similar poles are brought together? So if we try to bring these two similar poles of a dipole magnet together, this is a permanent magnet, these are the two dipoles, and we try to bring them together, then if north is brought close to north or if south is brought close to south, then they always repel each other. That means there is a repulsive force. So this magnetic property is very much similar to the electrical properties, where different charges attract each other and same charges repel each other. Similarly, for a magnetic dipole, same dipoles attract each other and the opposite dipoles repel each other. Now whenever we talk about magnetic poles, we always say magnetic dipoles. We never talk of magnetic monopole. Why is it so? Because whenever you are having a magnet, you will have two poles, north and south. As a single pole does not exist, that means there is no magnetic monopole. Now, why is it like that? Why there is no magnetic monopole? There is no magnetic monopole because we cannot isolate the north and south pole of a magnet. That means if you break this magnetic dipole into two parts, I'll break it from here, then again I'll have two parts of the magnet. This is the first half and this is the second half. But it is not like that. It is only the north and this is only the south. Now this will act as south and this end will act as north. So again there is a dipole. So we cannot isolate the north and south pole of a magnet. That is the reason there is no magnetic monopole. There is always a magnetic dipole. And the magnetic monopole does not exist. You know that there exist natural magnets, but can we design some magnets? Yes, it is possible to make magnets out of iron and the alloys of iron. So you can try it anytime and you try to convert them into magnets. Fifth and the most important point, that Earth also behaves as a magnet. Oh wow, our Earth behaves as a magnet. How come? Yes, because Earth behaves like a large dipole. It is a magnetic dipole which has North Pole and South Pole. And what about the magnetic field of the Earth? So our Earth behaves exactly like a magnet, and the magnetic field point approximately from geographical south to north. So the direction of the magnetic field of the Earth points from south to north. So that are all the daily observations or easy to get things for the magnetism. Now let's study something about bar magnet. So if we try to draw a bar magnet, then we have to draw two poles, North Pole and South Pole. So this is a permanent magnet and it acts as a magnetic dipole. And these two poles are similar to positive and negative charges that we have studied in electrostatic. This N we call as a North Pole and the S we call as a South Pole. And if you place some iron fillings around this bar magnet, you keep it vertical and keep some iron fillings around us, then you can see the magnetic field lines. What will be the pattern? Let's see. So if you keep bar magnet somewhere here in the mid, then this will be the pattern of the iron fillings. And you can easily observe it. Just take a bar magnet, place it vertically and keep some iron fillings, and you can easily see this pattern for the magnetic field lines. So can we see the magnetic field lines? Yes, this is the visible representation of the magnetic field lines. So what we conclude that magnetic field lines are visible and they have certain properties. So let us study about the properties of magnetic field lines. First property is that magnetic field lines of a magnet or of a solenoid, they always form continuous loop. So that is the first property. If you look up to the magnetic field lines of either a magnet or it was a solenoid is a long rod and a number of wires are wrapped around this. You want to go to the property of the solenoid, then you can go to the magnetism of moving charges. The link is given below this lecture. But if you find the magnetic field lines of either a magnet or of a solenoid, then you will always see some continuous loops. Second point is that the magnetic field is stronger. We use B to represent the magnetic field. So the magnetic field is stronger where the number of field lines crossing per unit area is more. That means wherever the density of the magnetic field lines is more, the magnetic field is stronger in that area. So if you have a more density of the magnetic field lines crossing in comparison to some other area where the magnetic field lines are small in number, then you say that the magnetic field is stronger in this area in comparison to this. So that is how the number of magnetic field lines decides the strength of a magnetic field. Third point is that magnetic field lines do not intersect. They never cross each other, and this property is similar to the electric field lines because electric field lines also do not cross each other anytime. So the magnetic field lines do not intersect. And what is the reason why they cannot intersect? Let us come to the fourth point and then I'll explain you why they cannot intersect. Fourth and the very important point is that at any point of the magnetic field lines, if you draw a tangent, then you will find the direction of net magnetic field B. So if there is any point where you want to know the direction of the magnetic field, net magnetic field at that point, then you have to simply draw a tangent to the magnetic field line, and the direction of tangent will give you the direction of net magnetic field. So that is why if there are two magnetic field lines which are intersecting each other or which are crossing each other, then if you draw a tangent at this point, then you will have two tangents. So these lines are crossing each other. So if at this particular point, if I want to draw a tangent, then for the first line, the tangent would be somewhat like this. And for the second point, the tangent would be like this. So this shows the direction of net magnetic field as well as this shows the direction of net magnetic field. So it is not possible for a single point to have two directions of the magnetic field. That is why there is no intersection of magnetic field lines, or magnetic field lines do not cross each other. Hope it is clear to you. So what we see is that all these properties of the magnetic field lines, they are very much similar to the electric field lines. They also form a continuous loop, and they're also in the electric field lines, whereas more density is a more electric field and there is a more magnetic field lines, that means a more magnetic field. Magnetic field lines also do not intersect like the electric field lines, and any point if you want to see the direction of the magnetic field, then you have to draw a tangent on the magnetic field lines. Similarly, if you want to draw the direction of the electric field, then you have to draw the electric field lines. A tangent will give you the direction of the electric field. So all these are the similarities between the magnetic field lines and electric field lines. So let us have a quick look at the magnetic field lines and electric field lines. So if you want to draw the magnetic field lines, then I have drawn two charges, positive and negative charges, and electric field lines, they always originate from the positive charge and they end up at the negative charge, because positive charge always has a sinks, because positive charge always acts as a source, as a thumb rule, and negative charge always acts as a sink, as a thumb rule. So our electric field lines will start up from here and they will end up at here. So if I start drawing, then I have to draw somewhat like this. So this is how we can draw electric field lines. They are always beginning from the source, a positive charge, and they are always ending towards a negative charge, acting as a sink. So that is how we can draw electric field lines. And now we want to draw the magnetic field lines. So in order to draw the magnetic field lines, we make a bar magnet. So this is our bar magnet. These are the two poles, magnetic north pole and magnetic south pole. And now we want to draw the magnetic field lines. So inside the magnet, they will start from south to north, somewhat like this. And outside, they will move from north to south. So that is how we draw the magnetic field lines. Here you can see two poles, north pole and south pole. So inside the magnet, inside the bar magnet, the direction is from south to north. But if you come outside the bar magnet, then the magnetic field lines always flow from north to south. That means they will start from north and they will end towards the south. So that is how we can show the electric field lines. Here we have taken a dipole, that is a positive and a negative charge. And here we have taken a bar magnet. So that is how you can see clearly the representation of an electric field lines and a magnetic field lines and the similarities between these two. Now we'll next move to certain derivations which are related to the magnetic field. So first of all, we will do the magnetic field of a solenoid, and then we'll do the magnetic field of a dipole. So let us first move to a solenoid. So solenoid is simply a long rod where a number of turns are wrapped around this, and electric current is flowing in these wires, so it will create a magnetic field. So let us first draw a solenoid. So this is a solenoid whose center point is O, and this is the axis of the solenoid, and the radius of the solenoid is small a. This I am showing it as here. And at a distance small r from the solenoid, we are taking any point. This is any point P from a small section dx. This is a small section. This length is dx of the solenoid. This is the center point and the radius is a. And this length, since we have divided into two halves, so I'll take each length as L. That means the total length is 2L for the solenoid. This is L and this is also L. So that is how we have drawn a solenoid. And say that if this is a polycylinder and a number of wires are wrapped around it, so we can take that small is the number of turns per unit length. That means small n is equal to capital N upon L. Here L is the total length of the wires and N is the total turns. So small n is the number of turns per unit length of wire. And the radius that is given is small a. We want to find out the magnetic field at point P. So this is point P, which is at a distance r from the small segment dx. O is the center of the solenoid. So let the center O is be at any point x. So if O is the center of the solenoid, then at a distance small x, we are taking any section dx. So this is the thickness dx of the solenoid. So within this 6 dx, as the number of turns per unit length is small n, so in the thickness dx, the turn will be n into dx. Hope it is clear to you. That we extended once again, that small n is the number of turns per unit length. And dx we have taken as any segment dx. This is the segment. So within this segment, the number of turns will be n into dx. And if you take I is the current which is flowing in the wire which are wrapped around this hollow cylinder. So I is the current which is flowing in the solenoid. Now we want to calculate the magnetic field at any point P due to this segment dx. So if you want to find out this, then you have to use the Biot-Savart's law. So if you want to use the Biot-Savart's law, and this is any cross section of thickness dx of this solenoid, and this is a cylinder. So if you take a cross section of the cylinder, that is always a circle. So this will be acting like a circular loop. And this will be the axis of the circular loop. So we can use the Biot-Savart's law for the magnetic field on the axis of a circular current loop. So we are writing Biot-Savart's law for magnetic field at the axis of a circular current carrying loop. Because this is due to a small segment, so the magnetic field will be dB. This is mu naught n IA square, but here we have the thickness as mu naught n dx. So mu naught n dx IA square upon 2. Now we have to take the distance. Now we have to take the distance of this section dx from the point P. Now the total distance of this from the center is r, and this is at a distance x. So if we do r minus x, then we'll have the distance between this segment and P. So here I am writing it down r minus x whole square, because r is the distance of point P from the center O, and x is the distance of the center and section dx. So if we do r minus x, we will have the distance between this section and point P. So this is r minus x squared plus a squared to the power 3 by 2. So in this case, we'll have dV as this. And what is the general formula? If you want to see the general formula, it is dV is equal to mu naught n I a squared upon 2 plus x squared to the power 3 by 2. So within this section, the terms will be n into dx, and here the distance is not x, this is r minus x. So this is the only change we have made. So in this case, using the Biot-Savart's law, this is the equation. So this represents the magnetic field due to this thickness dx. And if you want to get the total magnetic field, then we have to integrate. So to get the total magnetic field, that is the integration of all these small dB. So if you integrate all these small dB, you will have the total magnetic field B. Now what are the limits you have to put? Because it is starting from the L, then you have the center, and again it is ending at the L. So this is 0. So this length you can take as minus L, because that is on the negative side before 0 or before the center O. And here you can take it as plus L. So if you want to put the limit, then you can integrate it from minus L to plus L, because that is the total length of the solenoid. This side is L and this side is L. So it goes from minus L to L. Now put the value of dB. So we'll have Bs. Now take out all the constant outside the integration. Mu naught is a constant, n is a constant, I a square, all these are constant, and upon 2. These are the only constant. Now put the limit minus L, 2 plus L. Now what is left? Here it is dx upon, now r minus x square plus a square. This we have to integrate. Now if we take the distance r, which is very greater than the radius a of the solenoid, then you can neglect this term in terms of a. So a is very small, so this is, so a is very small, so this is only r is left. So r square to the power 3 by 2 will be r to the power 3. So you can again write it as b is equal to mu naught n I a square upon 2. Now this we have neglected, and this x is again small with respect to r. So you can take it as only r cube. Now it is very easy to integrate, minus L to L dx. And dx if you integrate, you will have x. And x if you put the limit L to minus L, then this will be L minus L, so it is 2L. So we have B as mu naught n I a square upon 2r cube, and here 2L. So this is expression for the magnetic field due to the solenoid, due to the total magnetic field due to the solenoid at any point P. Now we want to write down this equation in terms of the magnetic moment. What is the magnetic moment? Magnetic moment is defined with the term capital M, and this is equal to I into A, where I is the current flowing and A is the area. So I is already there, that is the current flowing, and area if you want to get, then you can write down areas, and this is the current I, and number of turns is small n per unit length, total length is 2L. So this is the number of turns, and each turn is having the area pi a square, because A is the radius of this solenoid. So this is the total area. Now we want to place this amps somewhere here in this equation. So I is already there, N is already there, 2L is already there, A square is already there. What we need is pi. So we have to multiply and divide with pi. So write down the equation of B, this expression again, mu naught n I A square upon 2R cube multiplied with 2L. So if you want to put M, then I is here, N is here, A square is here, and 2L is here. So we have to do pi a square, so multiply it with pi and divide it with pi. So what you will have? So this is equal to mu naught, then this whole thing, so all these things, this n I A square 2L pi, this will become M, and this is 2 pi R cube. Now what we know is a constant is mu naught upon 4 pi. So again, if we multiply and divide it with 2, you will have mu naught 2m upon 4 pi R cube. So that is our final result, that the magnetic field at any point P of the solenoid will be mu naught upon 4 pi 2m upon R cube. So always remember this formula whenever you have to calculate the magnetic field in terms of the magnetic moment and the axis of a solenoid. Then this formula is always standing very good. That P is equal to mu naught upon 4 pi 2m upon R cube. And this also has the similarity with the electric dipole. At the axis you have, it is 1 upon 4 pi epsilon naught 2p upon R cube. That is very much similar. So if you remember that formula for the electric dipole, you can easily remember it for the magnetic dipole. So both are similar. And there is one more thing, that this equation also holds true for the magnetic field of a bar magnet for far axial. If there is a point which is on the far axis of a bar magnet, then this will be the same field that is of a solenoid. So you can also use this formula when you are given with a bar magnet and there is a point on the far axis of the bar magnet. Then also the magnetic field B will be mu naught upon 4 pi 2m upon R cube. So this holds for axis of a solenoid. This magnetic field formula holds for the axis, any point on the axis of a solenoid or any point on the far axis of a bar magnet. And this is also the magnetic counterpart of the electric field due to electric dipole on the axis. So this is the same formula. In that case, we have E is equal to 1 upon 4 pi epsilon naught 2p upon R cube. And here we are having B is equal to mu naught upon 4 pi 2m upon R cube. So one formula and 3 times you can use it. And next we will do is that when we place a dipole in a uniform magnetic field. So let us quickly go there. So here we are using a dipole. So this is a dipole, north and south. And it is kept in a magnetic field, which is a uniform magnetic field. So we'll study dipole in a uniform magnetic field. So this is the direction of the magnetic field. So it is making any angle theta with the magnetic dipole. This is the direction of the uniform magnetic field. So why we have drawn a dipole like this? Because we have placed a small compass needle of magnetic moment capital M. So this is a compass needle whose magnetic moment is capital M, and magnetic moment is equal to I into A, and the moment of inertia is capital I. And we assume that this compass needle is oscillating in this uniform magnetic field. So if it is oscillating, that means there is a torque which is acting. So write down the torque which is acting on this compass needle. Tau will be m cross b, because m is a magnetic moment and b is a magnetic field. Since this is a cross product, so we can write it down as mb sine theta. Now here the torque which is acting tau is a restoring torque, which will try to bring this magnetic compass needle into its original position. So we call it as a restoring torque. And theta, because of the sine theta, and theta is the angle between the magnetic moment and magnetic field. Now if this compass is in equilibrium position, then now there is a torque which is acting, which is trying to align this along the direction of the magnetic field. And also there is a moment of inertia which is causing it to deflect. So whenever there is an equilibrium position, then this deflecting torque will be equal to the restoring torque. So this we have written as a deflecting torque because this is a moment of inertia and this is the angle theta through which it is deflected. So this we call as deflecting torque, and this is the restoring torque which is trying to restore the position of this compass needle. So when this compass is in equilibrium position, when these two are equal to each other. Equilibrium condition is when these two are balancing each other. So when these two torques are balancing each other, when these two torques are equal to each other, then our compass needle will be in the equilibrium position. So let us equate these two. As you can see here, this angle theta is very small. So since theta is very small, then sine theta is approximately equal to theta. So sine theta we can write down approximately equal to theta. So this equation will be I d2 theta upon dt2 is equal to minus mb theta, or d2 theta upon dt2 is equal to minus mb upon I into theta. Now since it is oscillating, then it is performing a simple harmonic motion. So it satisfies the condition of a simple harmonic motion, and we know that the equation for the simple harmonic motion is written as, if x is the displacement, then d2x upon dt2 is equal to minus omega square x. Here this is not a linear displacement, it is an angular displacement. So you can compare this equation, you can place theta in place of x. So d2 theta upon dt2 is equal to minus omega square theta. So if you compare these two equations, then our omega square is equal to mb upon I. Or if you take any under root, then omega is equal to under root mb upon I. So now we know the angular frequency, so we can calculate the time period because t is equal to 2 pi upon omega. So all the conditions of simple harmonic motions are satisfied. So we can as such use all the equations of simple harmonic motion, because time period t is equal to 2 pi upon omega and omega we have just calculated. So it implies t is equal to 2 pi under root I upon mb. I is the moment of inertia, m is the magnetic moment, and b is the magnetic field. So this is how we can calculate the time period of oscillation of this magnetic compass. And in this equation we have the magnetic field. So we can calculate b from here, just square this equation. So we'll have on squaring, we will have t square upon 4 pi square is equal to I upon mb. Or if you calculate b from here, then simply you will have the magnetic field B as 4 pi square I upon mt square. So this is how we can calculate the time period, and this is how we can get the magnetic field. Whenever there is a compass which is oscillating in the magnetic field, then the magnetic field is given by this equation, the time period of oscillation is given by this equation. Then the magnetic field is given by the following equation and the time period is given by this equation. And one more thing we can cover, and that is the potential energy, magnetic potential energy. So how can we calculate the magnetic potential energy? Let us see. Now for potential energy, we always use a symbol U. So same symbol we are using here. And since this potential energy is a magnetic potential energy, so we will use the suffix B. So UV. So if you integrate, because the torque is working for the deflection, so if you integrate this total torque, then you will have the potential energy, that is the work done. And the tau is m cross b, mb sine theta. So just put the value of tau. This is mb sine theta d theta. So mb is constant, it will be out of this integration. All you have to integrate is sine theta d theta. And the integration of sine theta is minus cos theta. So this magnetic potential energy will be equal to minus mb cos theta. And cos theta always symbolizes a dot product. So we can also write it down as minus m dot b. So the magnetic potential energy is always minus m dot b or minus mb cos theta. So if you put theta is equal to 0 degree, because cos theta is 1. So for 0 degree, the magnetic potential energy will have the value minus mb. And if you put theta is equal to 180 degree, then cos 180 degree is minus 1. So you will have the magnetic potential energy as plus mb. So this is the minimum value of magnetic potential energy at theta equals to 0 degree. That means when our compass needle is aligned along the magnetic field, then the potential energy is minimum, and that is the most stable position. So remember, the most stable position is when our magnetic compass is in the direction of magnetic field, and the maximum potential energy is when they are anti-parallel to each other, and this is the most unstable position. So you can write it down that for the theta equals to 0 degree, when our magnetic compass is in the direction of magnetic field, then the magnetic potential energy is minimum, and this is the most stable position, because according to physics, everybody wants to be in the minimum energy state. So this is the minimum energy, so that is the most stable state, and where the highest energy state is the most unstable state. So this is the most unstable state, or the most unstable position. So just remember all the simple laws of physics, that everybody wants to remain in the minimum energy state, and if it is in the minimum energy state, it is most stable. If it is in the highest energy state, it wants to get away from the highest energy state, and it is the most unstable state. And this is also equal to the and if you go to electrostatics, there also we get the electrostatic potential energy is P cross E. Here also, there also you will use in place of P, in place of magnetic moment, you are having the dipole moment, and here you are having the electric field. So that is also similar to the So whenever you are using electrostatics, then you have electrostatic potential energy UE as P cross E. So that is also similar to the electrostatics. If you remember the electrostatic potential energy, then you can also remember the magnetic potential energies. Here this is electric dipole moment, so here is a magnetic dipole moment. Here is electric field, so here it will be magnetic field. So there is much similarity. For what we have studied for the electric field is similar to the magnetic field. So let us quickly go to the what are all the analogies between the electric and magnetic field. Let us have a quick review, and then it will be much easier for you to remember. So we're going to write down the quantity, its electrostatic equation and its magnetostatic equation. Now what are the replacements we have to do? So we are moving from electrostatic to magnetostatics. That means our electric field will be replaced by magnetic field. First of all, our electric dipole moment will be replaced by the magnetic moment. And our constant 1/4 pi epsilon naught will be replaced by mu naught upon 4 pi. So these are the easy replacement we will do, and we'll write down the quantities. So first of all, dipole moment. So dipole moment is P here, and in magnetostatics, magnetic dipole moment is capital M. Sometimes it is shown as a small m. So it is always the magnetic moment. Mostly it is shown as capital M. Equatorial field, that is a field, that is a vertical field which is passing from the center of the axis, that we call as equatorial field, and when the distance r is very greater than the length L. So for the electrostatic we got it as minus P upon 4 pi epsilon naught r cube. Hope you remember, you should remember, you have done up with that unit. Then it is minus P upon 4 pi epsilon naught r cube. Now write down the magnetostatic counterpart. So yes, P is replaced with capital M. Minus will be minus here. And 4 pi epsilon naught is replaced with mu naught upon 4 pi. And r cube. And you are done with it. This is minus mu naught upon 4 pi r cube. The electric field at the Now the axial field, that is a field at any point on the axis of electric dipole or a magnetic dipole. So the axial field, also the condition is that when the distance r is very greater than the length L. So for the electrostatic we had 2p upon 4 pi epsilon naught r cube. Also remember this equation. Now make the magnetic counterpart. 2 magnetic moment is m, and right 4 pi epsilon naught is mu naught upon 4 pi and r cube. This is mu naught 2m upon 4 pi r cube, right. External field. Due to external field, when there is a torque is acting, then how we write it down in electrostatic? The torque in external field is acting is P cross E. If you keep a dipole in an external electric field, then the torque is acting is P cross E. Is the dipole, electric dipole moment cross multiplied with the electric field. If you write down the magnetic counterpart, then torque is equal to magnetic moment M cross magnetic field B. Right. This is that easy to write down. One more quantity we want to write down is external field. Energy in the external field. So the electrostatic potential energy was minus P dot E. Same quantities, only the negative sign and a cross product. So if you want to write on the magnetostatic potential energy, UB, it will be again minus magnetic moment dot magnetic field. So minus M dot B. So this is how, by replacing these simple quantities, we can write down the equation is same. So it is very much easy to remember all these. Let us have a quick revision. Dipole moment is P, here it is M. Equatorial field is minus P upon 4 pi epsilon r cube, here it is minus mu naught M upon 4 pi r cube. Axial field is 2p 4 pi epsilon naught r cube, here it is mu naught 2m upon 4 pi r cube. External field torque acting as tau is equal to P cross E, here it is acting as tau is equal to M cross B. External field energy is electrostatic potential energy is minus P dot E, and here it is minus M dot P. So this is how you can write out the magnetostatic counterpart of all the electrostatic formulas you have written. It is that easy to learn and that easy to remember, and you can do all the numericals very easy. If you are very much thorough with the electrostatics, you can very easily do up with your magnetostatics. The next we are coming is a very interesting thing, because in the electrostatics we have gone up with the Gauss law, and that is a very important law, and it makes the derivations very simple. It makes us solve all the numericals very simple. That is the beauty of the Gauss law. So if we can use Gauss law in magnetostatics, that will be equally good. So let us see if we can use that similar Gauss law for the electrostatics as we can use it for the magnetostatics with a simple replacement. Let us see. So let us go to the Gauss law with the magnetism. See, this Gauss law is my favorite, and you also make it your favorite because it works in electrostatic and it works equally well in magnetostatics. With a slight turn, let us see what is the turn. So first of all, we have to write down the statement for the Gauss law in magnetism. So what is the statement? The number of magnetic field lines leaving the surface is balanced by the number of lines entering it. So that is the first statement, that the number of magnetic field lines which are leaving through the surface, we are given with the surface, and the number of lines, magnetic field lines which are going away from the surface, it is equal to the number of lines entering it. That means it is balanced by the number of magnetic field lines which are entering into the surface. So what does it mean? There is a second statement. What does it mean? The net magnetic flux is zero through any closed surface. That means in the magnetostatics, if you are having any closed surface, magnetic field lines are going into it, coming out of it, then for this closed surface, the net magnetic flux is zero. In electrostatic, we have phi dot ds is equal to q upon epsilon naught, and if there is no charge enclosed, then it was zero. But in the magnetostatics, the total flux is always zero through a closed surface. So let us draw a closed surface. Within this volume, this is the closed surface. Delta S, I am saying is the surface, and this is the direction. This is the normal to the surface. So this shows the direction of the surface. And here we have the magnetic field. B is shown like this. Then if the angle between the magnetic field and the surface is theta, so delta S is the area element we have taken, and B is the magnetic field, and N cap shows the direction of the area element. So the theta is the angle between this area element and the magnetic field B. And this is our closed surface S, and delta S is the small area element within this closed surface. So the magnetic flux through delta S is given as, this is the magnetic flux, so we use phi B. Phi symbol always stands for flux, and if it is B, that means the magnetic flux. So del phi is equal to P dot delta S, that is from the Gauss law electrostatics we have studied. And if you want to calculate the total flux, it is phi B, that means you have to take a summation of all these small area element delta phi B, then you will have the total flux through the surface over all the area elements. So this is equal to summation over all the area element B dot delta S. So this total flux should be equal to 0. That is what the Gauss law for magnetostatics is, that the net magnetic flux is 0 through any closed surface. So here S is the closed surface, so the total flux, that is a magnetic flux, will always be 0 through all the area element delta S. What we had in electrostatics? In electrostatics we have already studied that the total flux E dot delta S is equal to Q enclosed upon epsilon naught. Q encloses the charge enclosed in the closed surface, and epsilon naught is the permittivity. But here there is no magnetic monopole, so there cannot be any monopole inside the closed surface. So since there is no magnetic monopole, so we have the summation B dot delta S is equal to 0. So that is the magnetic counterpart of the Gauss law. So this is our Gauss law for magnetism. The net magnetic flux is 0 through any closed surface. So just always remember this as a statement of Gauss law for magnetism. And this is a statement that the net magnetic flux is 0 through any closed surface.
So that's all for today. If you like this lecture, then like and share and subscribe to our channel Physics Class so that you can continuously receive notifications for more such interesting lectures. Thank you.